science, basically applying things like design thinking, systems thinking, systemic design. These are words that product designers, product managers would be knowing, but there's also a technical component to this, which is what I'll elaborate on. And I'll talk about the various just I'll just give a quick overview of the various life cycle technical processes that are used when you perform any systems engineering activity. And like I mentioned, there's a case study from the civil engineering field, the Oresund Bridge in Denmark and Sweden, which connects Denmark and Sweden. So I'll go over that. And to end the talk, I'll go over something which I am currently working on, prosthetics. And I'll talk about how I am applying my systems engineering principles to this particular application. Well, it's not exactly what I am working on, but it is a related field. So Professor Khatri already talked about it, but I'll just go over it again. I did my education in mechatronics from MIT Manipal, and I'm currently pursuing my MS in robotics at WPI. Aside from, I've been involved in robotics. I mean, a lot of fields of robotics. Well, field robotics as part of Master of Manipal, mobile robotics and industrial automation through, the IIT Bombay Yantra program, agricultural robotics, like you can see here, that was my final year thesis, and defense robotics. And right now, while at Booster, I'm doing prosthetics and human augmentation using soft robotics. So bunch of different fields, and the hope that has given me a pretty good outlook on how robotics as a field is shaped, because robotics as a field is pretty interdisciplinary. So there's very good chance for this sort of thinking to arise naturally, because usually systems engineering is something that is taught as a formal discipline, but then fortunately, because we are roboticists, this sort of thinking is something that comes to us by nature, which is something that is very good for us as a roboticist. And yeah, this is just a short overview. Those of you who might recognize this, I mean, I game a lot, so Call of Duty, Deus Ex, I really like both of these games, especially the way they approach the concept of using technology to enhance human capability instead of the current meta, which is sort of like, in case a human can't do it, you build something that can. Well, my way of thinking is, if a human can't do something, what can we do to enhance our own capability to do it, instead of building something brute for us? So that is the kind of reasoning that I like to move forward with while I'm pursuing my research. All right, so we'll start with the talk properly now. Products and systems. Now, when we talk, so before I begin, I would like to give a disclaimer that I have taken some liberties with the way certain jargon is used, and certain technical terms are used, because what I speak over here and what you might find out when you Google may or may not match. So I've tried to, it is kind of a creative liberty in the way I am presenting this. So don't worry about it, it'll all make sense as long as you get the fundamentals of the thing. Okay, so product design, product management, and system engineering are more or less interconnected to each other, in the sense that they all deal with the same fundamental process. You have an idea, and you have to realize that idea, bring it into the real world, and in the case of a business, you bring it to market. Now, the way they approach this core central idea of an end to end process is different. In the case of product design, so let's take yeah, let's take this what do you call this, spectacle case, for example, right? Now, the way this spectacle case is designed is obviously designed to appeal to my view, right? The texture on the case, the fast track logo on the top, the way it opens and closes, little things like that, that evoke a certain sense of desire. It makes me want to have this case. Or a better example would actually be the Apple iPhone, because from an objective standpoint, okay, this is kind of hot take, but it may or may not be as technically fast as the Android phones, but then it just looks good, right? It feels good, and which is why people like it so much. That's why people like to throw money at Apple so much. So that is, the product design aspect, the interface, the experience, playing on the user's desire to have that product, and the engagement with the product. Now, the product management is the logistics side of this thing, where okay, I have a product that I have designed specifically to satisfy a certain desire of the customer, but in doing so I shouldn't be compromising the company's bottom line, which is where you have things like product lifecycle management and things like that. Because when you bring a product from ideation to to production to utilization, and you go through the whole PLM cycle of you bring it to market. There's a early adoption period, then the maturity period, then the retirement period. Throughout this entire process, the company's bottom line should not be hampered, because at the end of the day, companies pursue profit. So as long as we're able to maximize profit while also satisfying the user, striking that balance is the job of the product manager. Now, the systems architect or the systems engineer has an entirely different can of worms to deal with. His or her their role is basically to keep the ship from sinking in a way. Because let's say the product design wants is really cool. Let's say we're designing a chair for people to sit on, right? And the product designer wants a very specific sort of design, because to the designer, he's not from an engineering background. Obviously they'd come from a more creatively oriented background. So they have really funky designs, very weird shapes. Obviously they might take ergonomics into mind, but then it looks kind of futuristic, kind of hippie in a sense. The product manager doesn't care about what the product is as long as it doesn't affect the company's profit. So he'll probably go like, okay, fine, this chair design is good, but you're telling me to use endangered wood. I mean, obviously that's endangered and I can't even buy that because I'll hurt my company's budget. So use something like plastic or something. You'll use PVC to make the chair. And the system engineer has to come in, step in and say, my guy, no, you can't use PVC because it can't support a person's weight. You have to strike a balance between the budgeting aspect and what looks good. So let's go with wood for a prototype, and then we'll switch over to some other material for prototype. So you can see the interplay between the product designer's needs, the product manager's needs, and the systems engineer's needs. Product designer is all about the pizzazz, the thing that you see on billboards. It should look good. The product manager is all about the back end logistics. We want to design this thing. How do we set up team processes? How do we set up timelines so that this is possible? And the systems engineer is responsible for making sure that the product is technically sound, is makes sense from an engineering standpoint. Now, when we start off with uh, this whole idea of, fine, I know I'm an engineer, I know how to, let's say, design a low pass filter, or I know how to design a gear, but then what do I do with this information? I have to use this somewhere, right? Now, when you use this in the context of a larger system like a product, for example, there are two types of thinking. One is the top down approach, and obviously the bottom up approach. Design thinking takes the top down approach, where you start off with the environment that you wish to introduce a product in. You empathize with the environment. So let's say let's designing a phone, for example, right? I would conduct market research on obviously current options in the market and current needs of the demographic that I'm trying to target. So let's say I'm trying to target the student population, which obviously is more cost conscious, but they also like Instagram. So you need to have a good camera as well. Or if you are trying to target working professionals who don't really care much about the camera, but they want battery life, and they want all the company related apps that they're working with to integrate very nicely. And obviously if you want to give your phone to a corporate, a DB program or something like that, then you'd want to have IT tools that interface very nicely with the phone as a whole. So that the empathization, empathy aspect. Once that's done, you get this whole list of requirements, just a general database that, okay, these guys might like this, these guys might like this. Then you whittle that down, you define what exactly you want to shoot for with your product. So then you have kind of a bulleted list, prioritized by what you actually want to target. So if you are targeting, let's say, just students, right? So Do you want to place a camera first, or do you want to place the cost first? Because there's obviously going to be a trade off in how you want to approach things that way. Then comes the ideation phase, where you brainstorm, you get some concepts out, different designs. uh, you see this most often in cars, but you have this for all sorts of products, where you have certain concept models, very hatke ideas in a way that are presented, and then the creative team kind of goes through each one and selects one which would be, selects a couple rather, which would be the best ones going forward. Then you prototype that design, or rather the list of the designs that you have selected, and this is where the actual engineering happens. So if we talk about a robot, for example, empathize would be, let's say, if we, let's take the case of warehouse automation, which I actually have later, but you empathize with, let's say, the warehouse automation companies, logistic companies, let's say, Blue Dart or something. You define what the requirements are. Maybe they want something focusing on speed or reliability. You have some concepts for the sort of mobile robot or the sort of system that you want to create to satisfy the requirements. You actually do it, and then obviously you go and test it. Maybe you have some closed pilot training or testing in a secluded area of the warehouse, so that the system works, and then you start slowly scaling up, incorporating feedback as you go, so on and so forth. So this is the way the product designer or the product manager would approach things. A kind of a top down approach, where we don't want to deal with the nitty gritty of, let's say, how we should integrate an I2C protocol into this robot, because that's not what the product manager's job or the product designer's job is. Their job is just to ensure that, okay, if I need this function, can I have this function? If yes, then okay, let's do it. If not, are there any alternatives? So just, giving a yes or no answer to the client, that can I do this? Yes. Can I do this? No. That is a design thinking approach. Now, the systems thinking approach, which is mostly what we tend to deal with, is where you view the thing not as a single entity like you would in the case of design thinking, but you view this as an entity which is composed of certain systems, or systems of systems. If you think, an SOS, system of systems, and then each system would compose its own, components, its own constituents, and you relate each system to each other, think about the connections between them, and then you break it down, decompose and define into the components that you have, and then you start integrating it back. Does this connection make sense? So if you go back to the ITC thing again, the product manager might say, okay, well, the client wants a Jetson, NVIDIA Jetson. So let's have an NVIDIA Jetson. But then the systems engineer would look at the connection between the Jetson and, let's say, any other sensors that are atop our particular solution. And then they would argue that no, I mean, if the client wants this sensor and they want this Jetson, they're incompatible. They can't work together. So we need to have something to work as an intermediary. If they really want these two, if they don't, then do they want the sensor to remain, or do they want the Jetson to remain? So that sort of technical trade-off is what you would think about as a systems thinker. uh, and then obviously you keep on integrating, refining, and then you have clearly defined this abstract idea that was being discussed about using the design thinking approach into a very concrete building, a very concrete Tetris looking stack of systems that are all interconnected to each other. Now, obviously, each has its own pros and cons. Design thinking is a very creative, very user oriented approach, and systems is a very, it's a very engineer based approach. But it helps to think about both of them as two sides of the same coin, because we actually do this naturally. If let's say you are trying to plan, what to get for your groceries for the week, right? So you ask, people in your family, what do you want to have for lunch, what do you have for dinner, uh do you want to have non-veg this week, or do you not want to have non-veg this week? Is there some festival coming up? So you're basically asking the users, right? You're performing this design thinking approach and trying to just get a list of stuff. Then you switch to the systems thinking approach, where you think, okay, fine, I have these recipes. Let's say I want some tandoori item, I want some, something paneer related. Now, does the shop near my place have it? If it does, is it cost effective for me to get it? Even if I do have it, do I have stuff in my house that is capable of making it? If I don't even have the appropriate utensil, there's no point even getting it. So you can see how I'm thinking of the relation between my utensil system of systems and my food system of systems. In the context of the design thinking, system thinking approach, so there are many ways you can go about it. It's a very free flowing thing, but if I were to kind of compartmentalize it, so this is how I would do it. This design thinking approach is very problem centric. It focuses on, okay, what is the problem that I want to solve? What is the problem that the user or my customer is facing? And it focuses on the outer applications, or how that product is expressed in the world with respect to your user experience, your ethics. In the case of in case of AI and robotics, ethics is a very big concern that's being raised right now, and obviously your client and stakeholder needs. The system thinking thing focuses on the actual solution. So organizing the various modules in your robot, your subsystems, things like that. It's a very inward looking process. Now, like I mentioned before, I have an example for mobile robots and I have another one for prosthetics. So I'll go over the mobile robot one first. So it's the same process that we kind of go over just as an abstract thinking approach. So let's say I know that I want to do a mobile robot, but so usually this is one thing that I've noticed. People tend to, uh, how do I put this? People tend to make a solution and then they start searching for a problem to stuff that solution in. So which is actually kind of an argument that I have against a lot of startups that are there right now. But okay, that's a topic for another day. If I have, let's say, I want to do something that's SaaS related, software as a service related. Okay, cool. What is the background of this approach? Like, if I want to do SaaS, where do I do the SaaS? Like, who do I target? What is the specific problem that I'm solving with my SaaS? If is there anything that's differentiating me from the other SaaS competitors? So that's something that you'd have to sit and think about before you actually go happy go lucky and actually start designing anything. So background and problem definition is something that I recommend everyone do. Even in your daily life, it's something that's very good to do, and it doesn't even need anything. You just sit, meditate for a while on the problem, and you've done it. You've done your background and your problem definition. So to give some context on where I've positioned my solution, my hypothetical mobile robotic solution. So the background is post COVID. Even during COVID, because of the lack of manpower, we obviously saw a very good, very massive boom in e-commerce, and that also brought about a demand for 24/7 operations, because consumer products aside, having on demand delivery logistics for essential components like maybe some medical devices or things like that is good to have, right? Now we know the background, we know this is the sort of intent that we want to kind of achieve with our solution. Now what context are we restricting our intent by? Because I mean, post COVID there were a lot of booms. Now in e-commerce itself, there are a lot of booms. So is there anything specific within this boom that we're trying to target? Are we trying to target something specific to just delivery aspect? Like, do you want to make a mobile robot to deliver, or do you want to make a mobile robot for uh, you know the warehouse operation, or do you want to make a social thing? So that is where you define your problem, your context, the restrictions within which you want to operate. So there is the problem that I want to address is obviously the warehouse automation problem, where warehouses were struggling to meet targets for obvious reasons because of the demand that was being placed on it. And obviously, it is too expensive to revamp those facilities fully, because there are solutions where you have these motorized shelves, but obviously, if you have this gigantic 100 200 acre warehouse, obviously you can't tear everything down and start again, because that warehouse is a continually operational thing, right? You have to keep moving on, keep upgrading it as you go. So mobile robots are a very flexible option for that. So which is exactly what I've written here in design thinking. Use mobile robots to boost productivity. And while obviously there would be some human labor, so there is the question of, will this robot take my job? And technically it would, but there is an opportunity for humans and robots to kind of collaborate on certain tasks. So let's say the mobile robot is doing most of the heavy lifting of certain things, but then you have a human that's kind of supervising it. So you can kind of retrain your existing staff, maybe transfer them to other departments where there's a need for human workers, like maybe the admin office or maybe HR or something like that. So That is the design thinking approach. Now we know where our robots are positioned, we know how they would be interacting with the outer world. Now we have to look inward. If I have a mobile robot, what would it be designed on? Like, what do I use as a base? Should it have six wheels? Should it have four wheels? Should it use mechanism wheels? Should it use omni wheels? Should it not use any wheels and use tracks instead or rails instead? So that is something that you would want to think about when employing the systems thinking approach. Any particular navigational aspect that you want to do, fleet management infrastructure, and do you want to outsource it or you want to build it at home? I mean, at home as an in-house. And systemic design kind of blends both of them, because you're thinking not only about the robot itself but also how the robot interacts with the outer world. So like I mentioned, you can have collaborative cells with humans, and maybe having mobile robots everywhere may not be such a very good thing. It's like the AI problem, right? Every company thinks that AI is this magic sauce you just pour on a problem and it magically solves everything, right? But obviously that's not how it works. You have to strike a balance between dumping new technology and staying with the old traditional conventional methods, because there is a moat in it. That's why it held up for so long. So that is what you would kind of go through as a beginner to this whole thing. Similarly, I'll just repeat the same process for prosthetics. So the background is, this sector is relatively untapped because only recently are we really unlocking the limits to this field. What with the advancements in robotics and medical sciences and all. But the current problem right now is obviously, especially for low limb prosthesis, you have to keep weight on it. And for amputees who have never felt this before, for obvious reasons, it is difficult to adjust to. It takes months, maybe even a year or more to kind of adjust to this weight bearing thing. For upper limb prosthesis wearers, it's easier, but it is more mentally taxing, because the natural dexterity that we have in our hands is very difficult to achieve with the prosthetic, at least right now. Um, or they're very expensive. Like, at least in the US, the cost of a normal prosthetic arm is probably at least 30 to 40,000 dollars. So that is like 5 lakhs, give or take, 5 lakh INR, and that's the minimum baseline. If you want a good one and not just a wooden stump that you would that can't be even called an arm. So obviously the natural procession of things is that you'd want to reduce the cost. You'd want to have a low cost prosthetic, which would be modeled, because in case you want to have certain attachments for doing certain things, like let's say you want to, for some reason, replace your hand with something specialized. Let's say you're a worker who is still able to do work with a prosthetic, but then you need access to a particular tool which is kind of difficult to manipulate with your prosthetic hand alone. So maybe you have a prosthetic with that tool that you're working with attached, so it's easy for you to just switch out arms and then just do that thing. uh, and when you're undergoing rehabilitation with your physio, obviously these things take time. Adjustment to your prosthetic arm or leg, it takes time. So trying to make that easier for both the physio and the patient is also one very essential factor. And on the systems approach, the design of the prosthetic arm or limb itself is very important, because having biomimetic mechanisms to enable more natural motion is obviously a top priority. Using sustainable materials is also very important, because these things are custom built to every person, because obviously every person is not the same. And when they grow out of a particular prosthetic, or they don't need a particular prosthetic anymore, you can't put it on someone else and call it a day, because even the sockets that these guys build for the prosthetic is custom to a person. So if it's possible for us to recycle anything, that'd be very good, because we'll reduce waste that way. And obviously, having AI assistance for the way we actuate things is also very good, or it could also be used for data purposes. So if the physio is able to analyze the motions of the arm throughout the day, they might be able to devise a better uh, rehabilitation plan for the patient. And obviously systemic design combines both of them. You could modify things around your house to better fit the actions that your prosthetic arm is capable of doing. Like, instead of having maybe a soft bottle, you could probably use a hard bottle since prosthetics aren't really dexterous. So it's easier for them to just clamp onto something. So it's easy for you to, let's say, drink water. Or you could probably have handlebars around the house just for support in case you're using a low limb prosthetic, which is also something that is done in the houses of the older people, senior citizens. They have these handlebars in and around the house for them to hold on to because it's difficult for them to walk around the house. So things like that, that can little systemic changes in and around your environment as well as a product that you're doing to kind of make this whole process easier to adjust to. Now we'll go into, so now that I've given you an overview, general overview of how this sort of thinking is enabled, I'll go over a more technical overview of how systems engineering as a process is conducted, and we'll go over the case study that I mentioned before. So, in a systems engineering activity, so you might find this to be very similar to the design thinking process, or those of y'all who are familiar with the PLM process, you might find things that are very similar to this, like maturity, disposal, things like that. And in a way, they are all interconnected. It's just, kind of repackaging the same thing, but in different viewpoints. Now, concept is what I defined before, where you define the problem, you have a problem space, which you uh, whittle down based on your stakeholder requirements. So you identify your stakeholders, like, these three people are my primary stakeholders, like these guys are the deal breakers for the product. And then you have other people whose needs are also important, but then they're not as important as, these top three people. So those are your stakeholders. You identify your stakeholders, you take a big bunch of requirements from them, what they want, and then you kind of craft a need statement, which is very similar to a problem statement, but it also kind of encapsulates the needs of the stakeholders. So if the problem statement is we have to build a bridge, now a need statement would kind of include we want to build a bridge with so if a problem statement is we want to build a bridge which uses suspension or something like that, a need statement would be we want to build a bridge which has suspension because this stakeholder needs this functionality, this stakeholder needs this functionality. So just the main requirement that actually dictates what sort of system that you're building. So that is kind of what a need statement is. Not an exact science, but there is an art to it again. So it comes from experience. uh, Development is the actual, so this is where you would apply your systemic design. So now that you have your requirements, you categorize them into things that are essential to the product aspect, things that are essential to the technical aspect, things that are essential to maybe the marketing aspect. Like maybe the stakeholder requirement would be we want our product to appeal to children, the K-12 education, K-12 children. So that would be more of a marketing aspect. Then maybe the stakeholder would want something that doesn't break if it falls. So that would be more of a technical aspect because you want to choose a material that doesn't shatter if it falls. So that way you think about your overall architecture, the various modules or the various subsystems in your design. In the case of a robot, if you take let's take a mobile robot again. So you have your drivetrain, you have your sensor stack, you have your navigation stack, you have your chassis, things like that. So all these different modules, these different subsystems would come in your architecture and design, and then each of them would have a requirement based on the stakeholder requirements that you received before. The operational requirements, as we'll now call them. So if the stakeholder wants, if the operational requirement from the stakeholder is that they want the robot to be able to do a zero radius turn, which is kind of just spin around in place. So then you'd select, the appropriate set of wheels and the appropriate drivetrain and the appropriate drive methodology to enable that. So, so I've shown how you can convert an operational stakeholder requirement into a system requirement, which also carries over to the production aspect because if I have this mechanism, I should be able to manufacture this first of all and manufacture this at scale, which is very important for a company. So system requirements and functional requirements are key to making that transition because if I have something which perfectly satisfies my operational requirement but I can't manufacture it, then there's no point. So I have to make a trade-off saying, telling my stakeholder like, guy, look, I can do this in theory, but then in practice it's going to cost this much because manufacturing this is a pain. Now if you want that, I don't mind, but the budget is going to shoot up. So do you want that? So most of the times the stakeholders say no, because money is kind mostly the driving factor in most projects. So that way then you'll have to kind of step down and choose a more cost effective alternative. Utilization is where once you've actually produced your system, you set it out into the field, see how it's operating. And for that you have certain things called operational concepts, which are scenarios that you have in which you place your system and see how it works. So in the case of a mobile robot, let's say you place it in a warehouse somewhere in the Himalayas. For let's assume for the sake of discussion that there's a warehouse in the Himalayas. You put your robot there. Now, is it able to operate in those cold temperatures? Maybe something fails. Maybe the sensors don't work properly because of the temperature difference. So you take those into account, and you kind of do thought experiments in the sense of uh, I put my system in various situations, various scenarios, and try to visualize the entire end-to-end thing. So let's say I have a product, I put it in some warehouse here, I put it, in a different warehouse there, I put it in a warehouse where there are more people who don't like that this mobile robot is there. So it's not just the technical system, but you also have to think about how introducing the system into a scenario can affect the existing framework. So that is where the operational concept, or ConOps, CONOP, ConOps is used. And using during this you also have certain performance requirements, like it should be able to operate within a certain temperature range. uh, it should be able to satisfy a certain speed limit, or it should be able to carry these weights at a certain speed, or it should have a certain mean time between failure, mtbf. So things like that. Support is also a very important aspect, because having a measure of effectiveness, how effectively this system that you've employed is satisfying your defined goals, is very important. Along with, in case this system has been maintained, what are the various methods you can do, methods you can employ to maintain that system. Because if I build a system, but I can't maintain it, then it's good. It's as good as dead to me, because I can't even maintain it. It's a one-use object. Why would I even invest in a system like that? Whereas if I invest in a system which may not satisfy all my requirements, but it is very maintainable, it's very reliable, then I would obviously want to prefer that. And I can always kind of substitute the needs that are not met with some other system. So that's not really an issue for me. I'd rather spend more on a system that works 100% of the time, but doesn't satisfy some things, than a system that works 0% of the time or 10% of the time but satisfies everything. That doesn't make sense to me, as not really as an engineer, but also as a customer, as an end user. uh, and once everything's done and you've reached end of life, knowing how to dispose of that particular system or replace that system with a new better system is also a very core key component. Because if you've built your entire framework out on a particular system, and that system becomes obsolete, but then you have no way of replacing it because you have to build an entirely new framework, then that's just poor thinking on your part. Because everything has to come to an end at some point, everything has to have change in some point. So you have to think about, if I have the system, this is going to get old someday, this is going to have to be replaced someday. So do I have a back door in place for that? Do I have something planned, or will I be able to plan something for that? If not right now, if I'm not able to do that right now, that is also a very important component. So these are the various life cycle stages, and these are the associated technical processes that are associated by and large with each stage. Now there is overlap in how you kind of deal with this whole thing. Like sometimes while you're still working on the concept, you can try to develop and produce certain subsystems just to see whether they're even feasible, because maybe there are some core conceptual features that depend on this particular thing, and you just want to make sure that this thing that everything else is based on is valid or not. Because if you make your entire concept model and then this particular module is not even feasible to develop or produce, then there's no point in making a whole concept model. It's just wasted effort. So you can have some overlap there. You can have some overlap in the production utilization bit where you have the first prototype sent out, and then while they are in the field, you get field data back from them so that you're able to tweak the production of the later models to be more efficient. So there's a lot of overlap between how these various stages are done. Okay, so I'll illustrate how we apply these life cycle stages and these processes to the case of the Øresund Bridge, which, for those of you that may not know, is a bridge that spans Copenhagen in Denmark and Malmo in Sweden. And this is actually a very interesting project because this is so as you can see, this is a bridge that starts from Malmo, but then it turns into a tunnel in the middle of the sea, and then it continues underwater till Copenhagen in Denmark. And this was a very interesting project because so it's featured on Nagios, I think Mega Structures, I believe, and it also has a couple world records as well. Like this is the longest cable stay bridge in the world. It's also, I think, the longest underwater tunnel in the world, and this is the first of its kind. Um, Plenty a bunch of other engineering marvels and achievements that the thing has accomplished. So I'll go over how um, we approach the entire end-to-end development of this bridge from a systems engineer perspective. Like this is how projects are done. So obviously this is a very large scale project, but you can think of this as applying to anything else that involves things that are working together. So robot can have complexity of this scale. It's just things are big, so we think it's complex, but in reality it's basically the same thing. You have certain systems that are interacting with each other. It's just that the scale of each system, the magnitude of each system is just very large. So uh, let's start with exploring the problem space, the concept stage of the life cycle. um, Now, the problem with the orison, which is the sound in their language, is so there's this very big span of water in between Copenhagen and Malmo, which historically used to be crossed using ferries, or these guys had to, I guess, go all the way around somewhere like that, if my memory serves me correctly. So obviously, once the car became more and more prevalent as a mode of transportation, they had to have a solution for this. And there were many solutions. Like ever since the 1800s, rather, there were proposals to build a bridge between Helsingør and Helsingborg, Copenhagen and Malmo, somewhere over here. To have some sort of underwater tunnel, some sort of bridge. The multiple proposals. But unfortunately, it's also a right idea but a wrong time sort of situation, because uh, there was an idea for a bridge over here, but then in the 1800s they didn't have the technology. Then in 1938, I believe, there was another proposal which came very close to actualization realization, but then being 1939 and whatever, World War II, so then that idea stagnated. And then it was only in 1991 where all the Nordic countries, they signed something called the Great Belt Treaty, which was where basically, the outcome of that was work actually started on trying to connect Denmark and Sweden through this through the Øresund. And so yeah, a bit of a tangent over there, but the economic needs of the stakeholders, which were Denmark and Sweden, were Denmark wanted, well, cheaper housing because it's a pretty small country, and that entire section of the country is pretty much cut off from the rest of the EU, the European Union. And Sweden has much better connection to the mainland, since it shares a very large border with Norway, whereas Denmark only has this little strip of land which connects to Germany below. So that way, land and connectivity, problems are there. Uh, and Malmo wanted access to the EU because this, Malmo, or rather Sweden, is pretty much, towards the northeastern side, more towards Russia, so it's not able to access the EU very effectively because there wasn't any connection to the rest of the EU. People would have had to fly out to Europe or something like that. So it was a mutual agreement, a win-win for each of them. Denmark would get access to cheaper housing over here. Malmo would get access to the European Union, so the job market would open up. So it was a mutual symbiotic relationship that they wanted to uh, cultivate. Now, the requirements that they had were, so I've already talked about it, but just to list them down so that we know what is it that we have to tackle. Obviously, they are different countries, so protection of national borders is very important. We can't have a very haphazard just build a bridge and call it a day, because you'd have to deal with things like your immigration border checks, things like that. And Denmark and Sweden, although they are part of the whole Nordic cultural landscape, so they're very similar. They are, after all, two different countries with different languages, different styles of driving on the road, different safety system, different systems as a whole. So you have to navigate the connections of these two cultures. So that's also one very important requirement, and with through this bridge. Uh, Now, if once when we are building a bridge, obviously, the ecology or the environmental factor also comes into play, because wherever there are man-made structures, the natural thing has to suffer at some point. Dams, they turn their surroundings into swamps. Bridges, they tend to break coral, things like that. So obviously, the environmental and conservation groups had concerns for that. Now, but the most difficult requirement was actually that of the transportation authorities, because uh, we had a very interesting dynamic that was occurring in Copenhagen and Malmo. So the Copenhagen International Airport in Denmark is very close to where the bridge was supposed to touch down on. And now, obviously, if you build, a bridge with those anchor points pointing up in the sky, planes are going to find it very difficult to navigate those things, because it's literally next to the bridge in a way. So so that was their first major restriction. We can't have anything pointing up in the sky near anywhere the airport, because that'll be a problem for both the planes who want to land, so it'll be difficult for them to land. And God forbid, were something to happen and a plane were to hit one of the bridge towers. Obviously, these towers are central points. If in one of them fails, the entire bridge is just going to go down. So you can think of the butterfly effect that would ensue from this entire thing. So uh, preventing risk due to nearby air and sea traffic, because that is a very well traveled sea route. So you need to have provisions for uh, your boats and ships to traverse. Uh, I think someone's raised their hand. If there are any question, I'll just address them at the end of the session, if that's fine. Um right. And right. So smooth transitions between two very different transport systems. Like I mentioned, they all drive on different sides of the road. Even their safety systems, like I remember this one point that the fire hydrants that they used were built differently in Denmark and they were built differently in Sweden. So if you have a fire hose, the valve connection point was designed differently in Denmark and defined differently in Sweden. So if in case a fire breaks out on the bridge, which country should go? Obviously, both countries would go, but then what if Sweden got there first? They won't be able to use their hose if it's designed using Denmark's infrastructure. Denmark can use Sweden's infrastructure, so that's also one consideration that they have to make. Even the air, the train traffic, because here we are dealing not just with road traffic but also trains. This bridge supports road and rail traffic, so uh, they had to have a system where these train conductors who speak different languages would be able to understand the signs, the rail signs on both sides of the bridge, because they'd be crossing the border every time. So for the bridge, there were a couple ideas which you can see here. The civil engineers might know this better than me, but the arch bridge is obviously a simple and effective solution. But the problem with that is this arch over here doesn't provide clearance for ships, that effectively compared to the other options on the list. So this was kind of ruled out because obviously, like I mentioned before, sea traffic was a very important component. Um, Suspension bridges were the next obvious choice, but then keep in mind that we are dealing with rail traffic here, and the rails need to be on rigid bases. Now, suspension bridges are non-rigid in nature because you're just kind of suspending these road segments, so you can't really put train tracks there. The next, the compromise over there was a cable stay bridge. So it does work fundamentally uh, the same as a suspension bridge, but then it's rigid by nature. So that way we are able to not only have the advantage of a suspension bridge where you have this clearance down here, but you're also able to have a rigid road segment, which can be conducive to trains and road traffic as well. Okay. Um, Right. So now that all this was done, the final concept that they had was a joint bridge and tunnel setup where from Malmo we would begin with the bridge, which would be a cable stayed double decker bridge. And sorry, once you reach the middle of the Öresund, it would transition into a tunnel. So as you get closer to the airport, like I mentioned, you have this requirement that planes can't you can't have towers near the planes, right? So they thought let's just convert this into a tunnel. And in the middle of the Horizon, they had this artificial island called the Pebble, where the bridge would transition into a tunnel. So the cars would have their own tunnel and the trains would have their own tunnel, and then they'd go into Copenhagen through an underwater tunnel, and then they disperse from there. So this was a very innovative idea for the time, and it was very risky as well for obvious reasons because a bridge in itself is a very difficult endeavor. A tunnel that to underwater in itself is a very difficult endeavor. Combining the two is going to be another hell in itself, engineering hell in itself. And not only that, you have to think about the supporting infrastructure as well because all this is definitely going to lead to a lot of digging up stuff which is going to impact the ecology, for flora and fauna in the region, the marine life in the region, uh, because you're dealing with commuters from different countries, train operators from different countries. You need to have a homogenized system, not for safety reasons, the fire hydrant thing that I talked about, communication. If there's an accident or some untoward incident, both countries should be able to communicate with each other using some certain mnemonics or some certain signals, so that both of them are in the loop with respect to what's going on. Because this is obviously a very expensive project, you need a toll plaza and the regular maintenance by both countries. So pretty standard. Now, so I kind of skipped over the development aspect because that would be better answered by the Nat Geo documentary on it. If you just search, Orison Bridge, Nat Geo, you'll probably get a video on YouTube that goes through the entire end-to-end process. They talk about things like how the environmental groups had set a limit on the amount of spillage that occurs due to dredging. Dredging is, where you dig up the seabed for this stuff. And then there was this one case where they couldn't. Um, I don't know if you may have seen this, but the way tunnels are made is they have this long, cylindrical bore sort of machine, and they just run it through the mountain. Uh, they weren't able to do that here for some reason because it just wasn't flexible enough to accommodate their requirement. So then they had to rely on this a tunnel segment sort of solution where they had to drop stuff down into the ocean and then connect everything underwater. So lot of stuff, and they found unexploded bombs from the World War II era while they were dredging. So they had to call an entire bomb disposal team to first defuse all the bombs in the region. They didn't even know, they found out after a metal detector went off somewhere while they were dredging. So that could have been very gruesome, but fortunately no one was injured in that incident. So things like that, very little aspects that made this thing very challenging. Oh, I forgot to cover this. Right. So once this was done, the utilization effects were obviously clear to see. We had better or border access between Denmark and Sweden. We had reduced travel time, and we had, obviously, people would prefer that more. And that way, they were able to achieve their uh, objective within budget, within timeline, and they were able to satisfy all the objectives that they had set out for themselves, which is also why the Nordic and Scandinavian countries are leaders in civil engineering. They really do their homework in that regard. Um, but yeah, this is just a summary of basically what I talked about. We have the concept, uh, the need for the system defined. We have the actual development of the system defined, where we define your specs, and we talk about how we approach those things. Production, where the actual, the physical groundwork is being done, on the floor work. Um, the utilization aspect, how the system would impact our environment, our end consumer. Support, like I mentioned, your fire systems, the road resealing in case, for maintenance purposes, debris clearance, when it snows over there. So obviously snow removal services, things like that. And having a retirement or, a break even point in mind. So obviously they've set the toll that way so that by around 2030, 2035, they should be able to pay it off entirely with the toll fee that they have in place. And then usually these structures are expected to last by at least 100 years, but let's see, depending on how things are going, it may last for longer, it may not last for that long. So that's all up in the air for that. Okay, so that was a bit of a scenic tour through how you apply systems engineering in a totally different discipline. So you can see that these concepts are basically the same. You start off with, you know what you have to do. You start off with who is involved in the project. You start off with and then you continue on with, okay, fine, you guys are the people who are benefiting from this project, but what exactly do you need? Then you take those into account. You process some ideas. You fixate yourself on certain idea, bits, implement them, see how it works. Can you maintain this thing, and more importantly, is it possible to replace this in the end? So I'll apply this again, but to a context that's more familiar to us, something robotic related. And this would be again prosthetics. uh, so this title, yeah, and there's also one more thing. The title is something that is usually kind of done at the end, because you sometimes don't really know what is it that you would be building until after you finish this whole aspect of the whole system engineering stuff. So right now I knew what I was doing, which is why I just put the title here, but then that's just something to keep in mind. Right, so this is just another reformulation of the whole process, just with different nomenclature. So uh, what I would do is research the literature, existing literature, see how current things are being done, understand the background that I want to target, formulate a need statement, identify your stakeholder and functional requirements, create an operational concept for this, plan your design and development of the system, and then you go through the systems engineering process again and again. So now I'll proceed to actually walk you through how I would go about such a thing. So to give some background, I haven't put this in this slide because it's quite a lot. But in the US, there are approximately 2 million people that are currently living with a prosthetic, or without, either born without limbs due to congenital defects, or maybe due to accidents that required amputation. So there's a lot of people like that. And like I mentioned before, prosthetics are very expensive. So most people just choose to go without it, or they choose a very low cost, thing that just works, but it's not something that they want. So, and because of this, there is this cascading financial loss that they experience. Because if I'm not able to work effectively using, my prosthetic, I would obviously be denied certain opportunities. I mean, denied the opportunity to excel in something, even though I'm capable of doing it, but I'm not able to because of this prosthetic. And that, that door closes, and then because of that you lose access to entire path of growth, which compounds itself to at least $400,000 wasted over a lifetime on average. So this is the estimate that has been given by the government for how much money are people living without limbs losing over a lifetime. So $500,000 is what, like 5 crores, 6 crores, I guess. So that is a lot of money. Uh, you can see why it's very important to address this, nip this problem in the bud. And also as so that's the financial aspect, but then on a day to day basis amputees cannot adjust to everyday life because, like I mentioned, there is a lack of aids to help them with your daily tasks. They don't have the exact prosthetic ability that they need. Why? Because money investment, prosthetics are expensive and they take time, because most of these prosthetics are made out of stuff like carbon fiber or metals that are very light, but they're difficult to kind of manufacture. And like I mentioned, the rehab process, things like that, it's very long and time consuming, which uh, and obviously once you, if you're an amputee, you can't uh, work as effectively if you're just sitting around waiting for the thing that is allowing you to work to arrive. So long rehabilitation lead times for your prosthetic. And the reason for that, the root cause for all this is you don't have a low cost alternative. You don't have a sustainable alternative. So you can see how from the main system, I was able to use people who've done lean or Six Sigma might know this as the 5 why approach, where you just ask, why, like 4 5 times, and then you get a root cause. So this is the actual reason why this is happening. So using this as a base, we are able to formulate a need statement like you could read here. Like I mentioned, the expensive long rehab times. So this leads to financial losses and value-based losses in the future. So because of that, you need a low-cost sustainable solution for shortening the acquisition, uh, quickening your therapy time so that amputees are able to integrate with society much faster. Then you identify your stakeholders and requirements. In this case, you have three main ones: your medicos, your doctors and physios and everything; your manufacturers, who would either be the manufacturing company that's building a prosthetic, or I thought we can try to do the 3D printing. So let's say the 3D printer companies, and obviously you have your patients who would be your end consumer. And you can see how I've demarcated their roles, their overarching roles. Quality assurance, ensuring that so their interactions with the other stakeholders would be verifying compliance. So manufacturers have to talk to these guys to ensure that they are not breaking any FDA or medical regulations or anything, and they would document the process of the patient so that they know that everything's happening as per code. And their requirements from the medicals are like, we want this thing to comply with FDA requirements, and we want to protect patient data, because obviously Hippocratic oath and everything, but there's also your patient privacy laws. So you don't want that information to get out for obvious reasons. uh, Manufacturers would be in your production category, and their interactions would be delivering the product to the patient and maintenance for the patient. So if there's any problem or if there's any uh, service related, they take care of that. And their requirements would be sustainable manufacturing, because manufacturers, they have to deal with the whole carbon footprint. So obviously they'd want to look for ways to tick that green net zero checkbox. So that is their main requirement, because they can't really dictate anything, because they just have to follow what the medical professional says. If the doctor says you have to make a prosthetic this way, they can't say anything. But at least their requirement is, okay, fine, we'll make this, but at least can you make it eco-friendly at least, or make it cheap for us to do it, or else why should we do it in the way. Now, which also applies to the patient, because the patient is the customer, and their interaction is consulting the medical professional to get their prosthetic done. And field testing, I field testing in quotes, because this data can be used by the manufacturer to make the prosthetic better, and it can be used by the medical professional to devise better rehab plans or something like that. And their requirements would be, this thing has to be easy to use. The user experience is a very big aspect, because this is something as part of your body now, and obviously reduce time and cost for the reasons that I mentioned before. uh so right. Now that we have these, we've demarcated the way these stakeholders interact with each other, we would separate the requirements, or rather filter these requirements through the lens of operational requirements, functional requirements, and performance requirements. So if I have, so you can actually see over here, let's take the first one. If my operational requirement, which came from my stakeholder, is this product must satisfy the FDA guideline, like it should be approved by the FDA. Not be approved by the FDA. So this is the operational thing. So when I'm in, so as a product, this thing should satisfy FDA approval. Now, what is it that constitutes approval by the FDA? So the FDA would probably say, if you want us to approve your thing, your systems should be functional enough to satisfy these particular ISO standards. 851. So it depends based on the device, but I've just put some general standards over here. So those of you all who are in the field might know better. Um, but yeah, you have functional standards for that. And then based, so this is kind of where it ends, at least for the compliance aspect. But then when it comes to the performance related aspect, so if we take let's say easy to install and remove, so this is a operational constraint that the customer has put. So the customer doesn't know, like it's not like they can say I want this to be done in 60 seconds or something. They'd be like, okay, fine, I just want it to be easy to install and remove. Now from the designer's perspective, we'll set a limit for ourselves, so to let's keep it, let's keep the install time less than 5 minutes, and we'll see if it's possible or not. And then that way we would be able to compare performance that way. Now similarly, if we have the operational requirement of comfortable usage, now for comfortable is subjective, but what we do know is that installation time definitely has a link to comfortable usage, because if it's easy to put and remove, so it's not a pain to use, obviously. Similarly, if the response time of that system is very fast, so if I think about closing my hand, but it takes like 1 second to close the hand, obviously that's not something that I want. It impacts my user experience. But if it's quick, if it's able to respond quickly to my actions, then that's something that's really good, right? So trying to filter the general subjective contextual requirements of the stakeholders through the lens of a system function, and then using that system functional requirement to evaluate its performance using some benchmark. So you can see how we get this big list of requirements that we're just told to, these this is what you want, process it. But then you look at the systems, look at how they interact with each other, and you find out that there are some functions that tend to satisfy multiple constraints. Like, if I have a usage time, if I have a cost, less than 30% of the total medical expense, it's sustainable because it makes sense. Like if I have I already have very high medical fees because, well, US healthcare. But or if I have to pay a lot more on top of that, then it's not a sustainable financial model for me. If it's very expensive to produce, it's not a very sustainable production model for me. And if I don't have all this, then it's not a very sustainable usage model for me. So you can see how the word sustainable can be approached from multiple different angles. And so yeah, this was actually my last slide. I thought there was another slide after this, but so you can see how we started off with the system science side of things. So I gave you an overview of how you begin to approach this concept. Then I walked you through the whole technicality of systems engineering as a field. What are the various steps in the process? We walked through the case study, and then I took something more robotics related. So hopefully this has been fruitful experience for you all, and from going on forward, you should be able to not only look at your current projects through this lens, but also your past projects. There is definitely scope for improvement in how you think when you look at past projects. I sure have seen that improvement in myself. So I hope this was very fruitful session for you all. And if there are any questions, then I can take them now.
Yeah, thank you, Nihal. for this very informative session. And now I request all participants, if they are having any questions or any doubts, or if they want something more information on the things or aspect explained by Nihal, then please do ask questions.
Hello, am I audible?
Yes, sir.
Yeah.
Yeah. So, hi Neil. Good talk, really informative. Especially for someone who isn't in the mechatronics field, pretty informative. I wanted to know, especially with systems engineering, how could someone who's not already like, what are like the prerequisites, like before I start exploring this avenue from a non-mechanic standpoint?
Okay. So fortunately, there's a lot of free online resources that can help you get started with it. So as a discipline, the pathway is obviously you have these. So you'll probably find this by different names, but you can start off by reading about design thinking, systemic design, systems thinking. Um, yeah, systemic design, something that I mentioned. Concepts of systems engineering or system science. You could start off by reading about that. Then, usually from there, once people have a general idea, they move on to this thing called model-based systems engineering. So, it takes the abstract principles that we've taken right now and applies it to a more concrete thing. So, this is very similar to so model-based systems engineering. People who are familiar with control systems might find the framework to be very similar because it's literally, you model your system as a set of inputs. uh, you have this system block that processes the input, kind of a transfer function in a way, and then you spit out some output, and that output goes to some other system block. So this process that I described is basically model-based systems engineering, where you have this process called a requirement mapping, where you're mapping stakeholder requirements to functional requirements of your system, and then those functional requirements are then mapped further down into component things like that. Project management is also, an applied form of systems engineering. So if you're managing a project, obviously you have to take care of how all your different teams are kind of working with each other. And if you think of each team as a system which is composed of, the components called people, you can apply these very same uh, principles. So as a field, you're able to kind of mix and match the core principles to any thing you want. But yeah, if you want to start off with, you can read up on the topics. I mean, you could take this talk as a springboard. You could look into model-based systems engineering, and I'm not sure if people would be able to access this, but there is this thing called, I think, International Council of Systems Engineers, or INCOSE, in COSE. So that WPI is a member of that, which is why I'm able to access their resources for free. But I'm not sure if they'll be that you'll probably find it somewhere. But that they have this thing called a Systems Engineering Handbook, which basically, kind of gives a very good overview of the field of systems engineering as a whole. And if you just search, systems engineering uh, materials online, you'll probably be able to find something like that. Because surprisingly enough, this is something that is taught in business schools. I found it very interesting because I saw the name systems engineering and I thought, coming from a robotics background, it feels natural enough. So I thought I'll look into it. But it tends to be something that business majors learn to get an insight into technical process. So we are going the other way around. We're from engineering background, we are going towards the overarching thing. But yeah, I hope that answers your question. And if for nothing else is YouTube, so you'll definitely be able to find something. But yeah, system science, MBSE, requirement mapping. If you search using these two three keywords, you should be able to find something.
Thanks again. Thanks for the talk, and thanks to RAS for the event.
Thank you.
Yeah, thank you, sir. If any other questions, please do ask. Okay, so I think Nihal has nicely delivered a session, specifically those who are interested to research and they want to explore the area of the system science, system engineering through the mechatronics, robotics, and all aligned areas. And he focused the major design thinking, system design, and then the mobile robots applications around that, and the most focused part while the development of the robotic, that is a sustainability. So he also focused on the design sustainability, that comfort as well as financially associations. So I think this is a sole package where the system engineering need to work, and likewise it will be a start for those who are looking for their masters and other research avenues in future. So I wish all the attendees good luck, and also we are very thankful to Nihal for taking this time out in early in the morning on a special request as a part of IEEE-RAS activity. So that is all from our side, and wish you good luck, Nihal, and all other participants. We seek your active participation in our upcoming lecture series. Soon in October, we are also planning to have one more expert from one of the renowned institution in India, who is specifically focusing on computer vision. And specifically, they have highlighted the research area in the computer vision. So we'll be shortly sharing the detail, and you all are requested to keep in touch. So you will also get to learn some of the upcoming areas where you can explore it out. And also in future, we'll expect some more talks from Nihal also, from that interdisciplinary things. So our students can get more and more what actually things are going on in the international platforms, specifically where they can hit in for their master's program, or if somebody want to see some international exposures as well as for the startups also. So it is much more interesting. And as we are knowing that more and more people are now interested to start their own venture, specifically this area has a wide scope. Okay,
Thank you.
so once again, thank
Actually,
you,
I'd want to
Nihal.
mention that since you mentioned research, so I'll want to say that the work that we do here at WPI, uh, the specific program that we have here, the core, so the NSF funded program that I'm in, the theme of our program is basically interdisciplinary research. So whatever, so technically researchers tend to focus on a single problem, but they don't go outside and see how this specific solution is going to affect the larger landscape. So that way we are kind of forced in a way to learn systems engineering by default. So
Yeah.
whoever's learning, who wants to get into research, this is a very good standpoint for you to understand how your particular research topic is impacting society. So that way you'll be able to not only make a better case for your own research, because in case you have to write grants, fellowships, so you have to prove to the panel that what you're doing is of very great importance. And if you're able to model that effectively quantitatively through systems and SE principles, that way you'll be able to make a better case for yourself and also kind of streamline your own research path that way. So
Yeah. Yeah, now also that as you mentioned that grant, so whatever the UN or international grants are there, so they are also asking for integrating that SDGs, Sustainable Development Goal. So that SDG is a major focus where we need to integrate that particular in our all grant applications if we are seeking from international agencies. So that is very nice, and thank you once again for very informative sessions. Okay, so I think with this, we reach the end of the session. Once again, thank you all participants, and Nihal, thank you. Thank you so much. Bye
thank
bye.
you everyone,
Good day.
have a good night. So I'll get
Yeah.
my day now. Okay,
Yeah.
see you, bye.
See you. Bye. Thank you.